Let's resume. I was gonna finish section 1 of this notebook in the previous video, but I failed to do so. Let's finish it now. What if we have nonlinear inequality kind of like that? This is far more complicated, and it's yes, I take it back. It's not that complicated this time, so graphical method will work. But in some other situation, graphical method will be really difficult to apply. So let's talk about analytical approach. Basically, this is a situation. We have 3 zeros given by the first factor equal to 0 when x equals to -3, and the second factor is equal to 0 when x equal to 0, and third factor is equal to 0 when x equal to 2. And the multiplicities are even for when x equals to -3, excuse me, odd for when x equals to 0, and odd for x equals to 2. So here is a diagram for the first number x equals to -3. I should have put -3 over here. So that's even multiplicity. X equal to 0 is the middle one, so that's odd multiplicity. X equals to 2 is the third 0, so that's odd multiplicity. As a matter of fact, I don't like it. Give me a moment. Okay, that's a lot better with all this labeling. I can clearly see that at x equal to -3 in this diagram, we have an even multiplicity, which corresponds to excuse me, this multiplicity. That's 2, so that's even. When x equal to 0, we have odd multiplicity 3, and x equal to 2, well, I don't have anything in this power, so 1 is hidden, so that's odd multiplicity. So starting from the right hand side end, when we have big number, then this expression is always positive. So we have positive in the right hand side of this diagram we have over here. Okay, I cannot highlight this, but in the right hand side. And then now what we do, we cross the first, the right hand side 0, excuse me, x equals to 2. Crossing odd multiplicity, we have changed signs, so next interval is negative. And then cross again, crossing 0, odd multiplicity, we have change of sign, so we have positive. And then crossing again to get final interval in the left hand side, keep the same sign because we are crossing even multiplicity. So what do we have? And we want this thing to be greater than 0, so I have to select interval where this thing is positive. We have 3 intervals in which this expression is positive. -∞ to -3, left hand side, and then -3 to 0, the next one, and then skip 0 to 2, and then go to 2 to infinity. And those are 3 intervals, so we could join them with union to get the solution set, and then that's gonna complete this problem. By the way, here is a graph of that function, and in this case we can see when the graph is positive, or y-coordinate is positive above the x-axis, or when y-coordinate is negative below the x-axis. But that was exception, and the reason we could see this beautiful graph and easily answer the question is because this problem was exceptionally simple. The kind of problems that show up in the exercise set of this notebook will not be that simple. By the way, let's do such problem. One such problem here, and here. No, not these. Here. Let's go ahead and do, let me see, a problem like this one. Okay, looks like all these problems are pretty simple actually. Okay, let's do this one. And then how do we handle that? Well, putting each factor equal to 0, we get 1, 2, 3, 4 linear factors equal to 0, so we get 4 zeros. And those 4 zeros are -1, 0, 3 halves, and 3 respectively. And their multiplicities are x equals to -1, that's even, and then x equal to 0, that's odd. X equal to 3 halves, that's odd. At x equal to 3, that's odd. So we have sign change at x equal to 3, x equal to 3 halves, x equal to 0, but no sign change at x equal to -1. And this diagram reflects that kind of behavior. We start from positive when x is greater than 3, when everything is positive. As we cross 3 times, we have sign change. And the last crossing at x equal to -1, we have to keep the same sign because x equals to -1 has an even multiplicity. We want these products to be less than 0, so we have to select intervals in which we have negative sign, and then there are 3 such intervals. X is less than -1, which means negative infinity to -1, and then the next interval -1 to 0, and then the next interval 3 halves to 3, and that's interval notation, which personally I prefer, to tell the truth. And here's a graph, and this graph is relatively simple too. I can clearly see in which interval the graph is above the x-axis and which interval graph is below the x-axis. Okay, maybe I'll have to cook up some problem in order to find out a problem that graph just doesn't tell you anything. Otherwise you do some creative zooming and this analytical method works. What if you have a problem that is given in, well, expanded form? You have to factor this polynomial first, kind of like this, and then put it into something like this, and then you get the zeros, and then you can go ahead with the sign analysis. This time the right hand side interval is negative because of this negative sign. When x is really big, all these products will be very well positive, but extra negative sign is there, so we have to start from the negative sign and then just do the same thing. As we cross odd multiplicity, change sign, cross even multiplicity, keep the same sign, cross odd multiplicity, we change sign, and so on. And we have to find out where this thing is positive, so find out the intervals in which we have positive sign in that diagram. Infinity, 0, union, 0 to 2, kind of like that. Okay, getting warmer. Let's move on to rational inequalities this time. Excuse me, no, before that, let's talk about semi-inequality. Okay, let's do this one. We have plenty of time. Semi-inequality, and we're in a similar situation as before, and then actually very same situation as before. Very same situation as problem B, which we already did. Excuse me, sorry about my cough. And then we have the same diagram. However, this time we have semi-inequalities. So this factor is allowed to be equal to 0. So when x is equal to -1, 0, or 3 halves, or 3, then we have an equality. This thing equal to 0 because 0 times anything is 0. So they are all included. In other words, we have solution x equals to 0 and 3 halves included. So getting all those positive, we have let me see, let me write down the solution here. 0 to 3 halves, and then union 3 to infinity, And it looks like this is a solution set. This is a solution set, but be careful actually now. 0 to 3 halves, okay, closed intervals because 0 and 3 halves are included. And 3 halves to infinity, that's okay too. X equal to 3 is allowed because we have equality. But as for equality, we forgot one. X equal to -1 is also a possibility. X equal to -1, then this factor becomes 0, so we have 0 equal to 0. So we have to consider x equal to -1 as well, and that is done like this. So we use the set notation here to represent a single point, and then this interval, and then that interval. And a lot of students actually miss this x equal to -1, but that's going to be a bit of a deduction. Here is the graph, by the way. When we have positive sign, 0 to 2/3, and then 3 to infinity, that's when the graph is positive. But when x equal to -1, please note the graph hits the x-axis even though it bounces back. So semi-inequalities can be a little bit tougher. Now let's move on to rational inequalities. And strict rational inequalities are simple enough, so I'm going to leave those to students. And how to factor the numerator and denominator, again, I'm going to leave those to students. So let's move on to problems like B. Okay, let's put all those factors, there are 4 factors, and then set those equal to 0, and you got x equal to -2, x equal to -1, x equal to 0, and x equal to 3 halves. And then we have, where's my diagram, kind of like this. But then again, we have a little bit of difficulty here. Now numerator is allowed to be 0. When x equals to -2, then this factor will become 0. So we have 0 times something that's equal to 0, so we have equality. Equal to 0, that's okay. But for example, x is equal to -1, this factor is equal to 0, but that's in denominator. And denominator is not allowed to be equal to 0. So everything breaks down, which means I have to expunge x equal to -1 out. And x equal to -2, that's okay. X equal to 3 halves, that's coming from the numerator, so that's okay. X equal to 0, we have to expunge that out because it's coming from denominator. And we have some diagram like this. Please note that x equal to 0 case and x equal to -1 case are expunged out, and we see those in this hollow dots. And x equal to 3 halves and x equal to -2 are solid dots, meaning those are the parts of those points are included in the solution set. And then apply the same sign analysis, starting from positive sign on the right hand side, and then use multiplicity. Change the sign when odd multiplicity, keep the same sign in even multiplicity. Change the sign, odd multiplicity. And finally, we have an even multiplicity, so keep the same sign. And then finding out intervals in which we have greater than or equal to 0, we get, let's see, we get -infinity to -2, and then -2 to -1, and -1 should not be included because it's coming from denominator. We talked about that. And then 3 halves to infinity, you have some interval kind of like this. And let's see, I don't have to worry about x equal to 0 there, it's expunged out. And now, because x equal to -2 has bracket, these two can be joined, and then we can put all these into single interval and then write as -infinity to -1 right away. And here is my final solution set here. If you have strict inequality, then you don't have to worry about the top or bottom. And all those points, those zeros are going to be excluded anyway. We have hollow dots all around, so this kind of thing is much easier. When semi-inequality takes place, you have to be extra careful about denominator versus the numerator.